Create your own 8x8x8 LED Cube 3-dimensional display. We believe this Instructable is the most comprehensive step-by-step guide to build an 8x8x8 LED Cube ever published on the intertubes. It will teach you everything from theory of operation, how to build the cube, to the inner workings of the software. We will take you through the software step by step, both the low-level drivers/routines and how to create awesome animations. The software aspect of LED cubes is often overlooked, but a LED cube is only as awesome as the software it runs. About halfway through the Instructable, you will actually have a fully functional LED cube. The remaining steps will show you how to create the software. A video is worth 1,000 words. I'll just leave it up to this video to convince you that this is the next project you will be building. I made this LED cube together with my friend Chiller. The build took about 4 days from small-scale prototyping to completed cube. Then another couple of hours to debug some faulty transistors. The software is probably another 4 to 5 days of work combined. At first glance this project might seem like an overly complex and daunting task. However, we are dealing with digital electronics here, so everything is either on or off. I've been doing electronics for a long time, and for years I struggled with analog circuits. The analog circuits failed over half the time even if I followed instructions. One resistor or capacitor with a slightly wrong value, and the circuit doesn't work. About 4 years ago, I decided to give microcontrollers a try. This completely changed my relationship with electronics. I went from only being able to build simple analog circuits, to being able to build almost anything. A digital circuit doesn't care if a resistor is 1k ohm or 2k ohm, as long as it can distinguish high from low. And believe me, this makes it a lot easier to do electronics. With that said, there are still some things you should know before venturing out and building this rather large project. You should have an understanding of basic electronics. We would recommend against building this as your very first electronics project. But please read the Instructable. You'll still learn a lot. How to solder. How to use a multimeter, etc. Writing code in C, optional. We provide a fully functional program, ready to go. You should also have patience and a generous amount of free time. Here is what you need to make a LED cube. 512x LEDs, plus some extra for making mistakes. 6 4x resistors. See separate step for ohm value. 1x or 2x large prototype PCBs. The type with copper eyes, see image. 1x 8MGA32 microcontroller, you can also use the pin-compatible 8MGA16. 3x status LEDs. You choose color and size. 3x resistors for the status LEDs. 8x74HC574 ICS. 16XPN2222 transistors. 16X1K resistors. 1x74HC138 IC. 1x Maxim MAX232 IC. 1x 14.7456 MHz crystal. 2x22PF ceramic capacitors. 16x 0.1 UF ceramic capacitors. 3x1000 UF electrolytic capacitor. 3x10 UF electrolytic capacitor. 1x100 UF electrolytic capacitors. 8x 20-pin IC sockets. 1x 40-pin IC socket. 2x 16-pin IC socket. 1x 2-pin screw terminal. 1x 2WIRE cable with plugs. 9x 8-pin terminal pins. 1x 4-pin terminal pins, right angle. 2x 16-pin ribbon cable connector. 1x 10-pin ribbon cable connector. Ribbon cable. 2x push buttons. 2x ribbon cable plugs. 9x 8-pin female header plugs. Serial cable and 4pin female pin header. Piece of wood for template and base. 8x optional pull-up resistors for layers. 5V power supply, see separate step for power supply. Total estimated build cost, $67 US. See attached price list. We see a lot of people asking for part numbers for Digi-Key, Mouser, or other big electronics stores. When you're working with hobby electronics, you don't necessarily need the most expensive components with the best quality. Most of the time, it is more important to actually have the component value at hand when you need it. We are big fans of buying really cheap component lots on eBay. You can get assortments of resistor, capacitors, transistors, and everything in between. If you buy these types of assortments, you will almost always have the parts you need in your part collection. For $17 you can get 2,000 resistors of 50 different values. Great value, and very convenient. Try doing some eBay searches and buy some components for future projects. Another one of our favorite stores is Futurelic. http://www.futurlec.com/right. They have everything you need. The thing they don't have is 1,000 different versions of that thing that you need, so browsing their inventory is a lot less confusing than buying from those bigger companies. A LED cube is like a LED screen, but it is special in that it has a third dimension, making it 3D. Think of it as many transparent low-resolution displays. In normal displays it is normal to try to stack the pixels as close as possible in order to make it look better, but in a cube one must be able to see through it, and more spacing between the pixels, actually its voxels since it is in 3D, is needed. The spacing is a trade-off between how easy the layers behind it is seen, and voxel fidelity. Since it is a lot more work making a LED cube than a LED display, they are usually low resolution. A LED display of 8x8 pixels is only 64 LEDs, but a LED cube in 8x8x8 is 512 LEDs, an order of magnitude harder to make. This is the reason LED cubes are only made in low resolution. A LED cube does not have to be symmetrical, it is possible to make a 7x8x9, or even oddly shaped ones. This LED cube has 512 LEDs. Obviously, having a dedicated I/O port for each LED would be very impractical. You would need a microcontroller with 512 I/O ports and run 512 wires through the cube. Instead, LED cubes rely on an optical phenomenon called persistence of vision, POV. If you flash a LED really fast, the image will stay on your retina for a little while after the LED turns off. By flashing each layer of the cube one after another really fast, it gives the illusion of a 3D image, when in fact you are looking at a series of 2D images stacked on top of one another. This is also called multiplexing. With this setup, we only need 64, for the anodes, plus 8, for each layer, I/O ports to control the LED cube. In the video, the process is slowed down enough for you to see it, then it runs faster and faster until the refresh rate is fast enough for the camera to catch the POV effect. We are going to be talking about anodes, cathodes, columns, and layers, so let's take a moment to get familiar with the anatomy of a LED cube. An LED has two legs. One positive, the anode, and one negative, cathode. In order to light up an LED, you have to run current from the positive to the negative leg. If I remember correctly, the actual flow of electrons is the other way around. But let's stick to the flow of current, which is from positive to negative for now. The LED cube is made up of columns and layers. The cathode legs of every LED in a layer are soldered together. All the anode legs in one column are soldered together. Each of the 64 columns are connected to the controller board with a separate wire. Each column can be controlled individually. Each of the 8 layers also have a separate wire going to the controller board. Each of the layers are connected to a transistor that enables the cube to turn on and off the flow of current through each layer. By only turning on the transistor for one layer, current from the anode columns can only flow through that layer. The transistors for the other layers are off, and the image outputted on the 64 anode wires are only shown on the selected layer. To display the next layer, simply turn off the transistor for the current layer, change the image on the 64 anode wires to the image for the next layer. Then turn on the transistor for the next layer. Rinse and repeat very fast. The layers will be referred to as layers, cathode layers, or ground layers. The columns will be referred to as columns, columns, or anodes. To drive a LED cube, you need two sets of I/O ports. One to source all the LED anode columns, and one to sync all the cathode layers. For the anode side of the cube, you'll need X2 I/O ports, where X3 is the size of your LED cube. For an 8x8x8, x equals 8, you need 64 I/O ports to drive the LED anodes. 8x8, you also need 8 I/O ports to drive the cathodes. Keep in mind that the number of I/O ports will increase exponentially. So will the number of LEDs. You can see a list of I/O pin requirement for different cube sizes in Table 1. For a small LED cube, 3x3x3 or 4x4x4, you might get away with connecting the cathode layers directly to a microcontroller I/O pin. For a larger cube, however, the current going through this pin will be too high. For an 8x8x8 LED cube with only 10 mA per LED, you need to switch 0.64 ampere. See Table 2 for an overview of power requirements for a LED layer of different sizes. This table shows the current draw with all LEDs on. If you are planning to build a larger cube than 8x8x8 or running each LED at more than 10-ish mA, remember to take into consideration that your layer transistors must be able to handle that load. We gathered from the last step that an 8x8x8 LED cube requires 64 plus 8 I/O lines to operate. No AVR microcontroller with a DIP package, the kind of through-hole chip you can easily solder or use in a breadboard, dual inline package, have that many I/O lines available. To get the required 64 output lines needed for the LED anodes, we will create a simple multiplexer circuit. This circuit will multiplex 11 I/O lines into 64 output lines. The multiplexer is built by using a component called a latch or a flip-flop. We will call them latches from here on. This multiplexer uses an 8-bit latch IC called 74HC574. This chip has the following pins. 8 inputs, D0-7. 8 outputs, Q0-7. 1 latch pin, CP. 1 output enable pin, OE. The job of the latch is to serve as a kind of simple memory. The latch can hold 8 bits of information, and these 8 bits are represented on the output pins. Consider a latch with an LED connected to output Q0. To turn this LED on, apply V+1 to input D0, then pull the CP pin low, G and D, then high, V+. When the CP pin changes from low to high, the state of the input D0 is latched onto the output Q0, and this output stays in that state regardless of future changes in the status of input D0, until new data is loaded by pulling the CP pin low and high again. To make a latch array that can remember the on/off state of 64 LEDs, we need 8 of these latches. The inputs D0-7 of all the latches are connected together in an 8-bit bus. To load the on/off states of all the 64 LEDs, we simply do this: load the data of the first latch onto the bus. Pull the CP pin of the first latch low then high. Load the data of the second latch onto the bus. Pull the CP pin of the second latch low then high. Load the data of the third latch onto the bus. Pull the CP pin of the third latch low then high. Rinse and repeat. The only problem with this setup is that we need 8 I/O lines to control the CP line for each latch. The solution is to use a 74HC138. This IC has 3 input lines and 8 outputs. The input lines are used to control which of the 8 output lines that will be pulled low at any time. The rest will be high. Each out the outputs on the 74HC138 is connected to the CP pin on one of the latches. The following pseudocode will load the contents of a buffer array onto the latch array. // port A equals data bus. // port B equals address bus, 74HC138. // char buffer 8 holds 64 bits of data for the latch array. Port B equals 0x00, // this pulls CP on latch 1 low. 4, I equals 0, I8, I++. Port A equals buffer I. Port B equals I+1. The outputs of the 74HC138 are active low. That means that the output that is active is pulled low. The latch pin, CP, on the latch is a rising edge trigger, meaning that the data is latched when it changes from low to high. To trigger the right latch, the 74HC138 needs to stay one step ahead of the counter I. If it had been an active high chip, we could write port B equals I. You are probably thinking, what happens when the counter reaches 7? That would mean that the output on port B is 8, 1000 binary, on the last iteration of the for loop. Only the first 8 bits of port B are connected to the 74HC138. So when port B outputs 8 or 1000 in binary, the 74HC138 reads 000 in binary, thus completing its cycle. It started at 0. The 74HC138 now outputs the following sequence, 1 2 3 4 5 6 7 0, thus giving a change from low to high for the current latch according to counter I. There is another solution for providing more output lines. We went with the latch-based multiplexer because we had 8 latches available when building the LED cube.